So thank you all so much for being here. Now, when we look, let me start with you, if I might. This is not around the corner, but it's maybe a longer corner we have to look at. But where do you think, in terms of reality, are we from the widespread use of, nuclear fusion? People talk about 2030, 2035 timelines. This is obviously, there's still a lot of challenges, still a long road to go. Give us a feel for, what do we have to do to get there?
Right. So, fusion, specifically in terms of 2030 timelines that you're speaking about, is already set in motion. So there's going to be net gain from fusion reactors, specifically tokamaks, in 2030s. Large purchase agreements across the world have been being made with data centers, with software companies who are going to be purchasing fusion energy. So that's on the timelines perspective. But globally, what's really changing is there's a spin-off of federal research that's moving to startups and faster ecosystems that are now making commercialization tech out of the research that's got into fusion.
So but give me a feel for the challenges that are there, because it needs to happen, from what I'm reading about, it needs to happen faster, but give us a feel for where the big challenges lie right now.
Right. So currently, the largest challenges in fusion are not around plasma performance, are not around if we can do fusion. It's more about how do you not melt your reactor? How do you make sure you've got enough exhaust out of the reactor? How do you have reliable performance? And that's more on the manufacturing and engineering side of things.
And we got two gentlemen who can maybe answer that for us too.
Yeah, actually, both of these gentlemen come from industries that have been developing solutions for nuclear fission, for aerospace, for defense, and across the board. And what we've really started seeing in fusion is we know how plasma or the fuel will react.
Right.
We are able to control that. But how do we make these systems more reliably and more, how does the manufacturing around that work, which we are learning from other industries. That's where we are at.
All right, I'll come back to you on that. Raghavan, when we look at, fusion plants, clearly they're going to be first of a kind, and any first of a kind project comes with a big price ticket, a lot of complexity. The politicians are getting excited about it. The communities are getting excited about it. You have to put all this together. Now, as an EPC and owner engineer, what would you say are the big top execution risks, I suppose, that really lie, and how do we avoid them in the design phase? There's an awful lot that has to be done to get there.
Yeah. First of all, thanks for the opportunity. Yeah, when we talk about nuclear is one of the clean source of energy. Definitely, we need nuclear. We have been focusing on fission for the last 40, 50 years.
And there is a lot going on in India right now, isn't there? And great projections for what's to come.
Correct. We have been focusing on fission reactors for last 40, 50 years. Once that technology is matured, now the focus is shifting to nuclear fusion. As you have rightly pointed out, any first of its kind project and the project of this complexity would have a lot of challenges, engineering challenges, because we are designing many systems for the first time. We are not aware of material properties, how the system is going to behave thermally, hydraulics, and so many other things. So every system we are doing for the first time. So that is the big challenge. And also we need to develop the ecosystem for supply chain ecosystem also is required. So now we have moved to large extent in engineering and supply chain related, but still a lot of challenges are there in terms of achieving commercially viable electricity source. So that challenge is going to be there, and the work should happen towards that.
It must be an engineer's dream, because I think you look at the work engineer has been doing for many years. Okay, not that you're doing the same thing every day and technology is moving, but the challenge that's there, I mean, this must be just a big shift upward for everyone. Yeah, it's a dynamic time.
Correct.
I'll come back to you on that. But Niraj, talk to us, when we look at, fusion and the discussions around it, we're looking at a breakthrough science. We really are. And when we look at the deployment, we need manufacturing at scale, on the material side. You're an expert in this already in terms of what you're doing. But how can India's manufacturing sector, what do we need to be doing to make sure that we get the design right and ultimately be able to deliver what's needed?
So I think it's an interesting time where you have both fusion, and I won't use the word nuclear fusion because globally people are moving away from associating it with the word nuclear. So we just call it fusion energy. But a lot of the fusion energy requirements for manufacturing draw upon the same requirements for fission and SMRs.
Right.
With the activity happening on both ends and the number of startups and programs that are being announced, there's a real challenge of capacity. So one of the things that India needs to do and companies in India need to do is really invest to scale up capacity so that you can become an important kind of contributor to the entire ecosystem, whether it's fusion energy, whether it's SMRs. So I think capacity constraints are going to hit the pace at which things actually get realized.
But the materials as such are manageable. What the work that you're doing already within space, within
correct. So a lot of the materials that
already
are being used in the initial prototypes are all drawing from what has already been made for conventional fission reactors. And these are special high temperature materials. And of course, there is always improvement that's ongoing for the next generation of reactors. But I don't think materials is a constraint for the initial prototypes that are being built all over the world.
And that's good to know. Raghavan, you're already working within this. I mean, there's a few projects around the world. We look at ITER in France, we look at the US, we look at even UK. So we're getting there. But talk to me just a little bit, about what's happening in France. And the ITER project in France, we're looking at 7 major partners: China, the EU, India, Japan, Russia, South Korea, and USA. So big partners there, but great that India is part of this.
Yes.
Bring us up to date in terms of the work that you're doing already there.
Yeah. Currently, this is one of the largest nuclear fusion project in the world, most ambitious project. It is a multi-governmental collaborative project. As you have mentioned, US, Russia, China, India, all are contributing. So India is also one of the member country contributing for the ITER nuclear experimental reactor project. And TC, we have been doing the complete detail engineering for that project, civil and structural design, piping, mechanical design, electrical, C&I design. So as of now, as we speak, 50 to 60 engineers from our organization is in ITER France, and almost 50, 60 engineers are working from India. So I would say 100 engineers are working for the last 6 years to make this project a reality. And this is the largest fusion device, magnetic containment fusion device with we call this as 10x. That means it will produce 10 times the electricity based on the X input is given, but it will produce 10 times the heat output. So that is called a 10x thing. This is the largest thing. And India is contributing about 9% in terms of investment. And we have the full IP rights once the project is completed. So I would say I visited that site 3-4 months back.
Wow.
And I visited a couple of years back.
Is there a bit of a wow factor in the place?
Yes, huge amount of construction has happened.
Wow.
All the civil, mechanical construction has been done. Now it is only electrical C&I part to be done. And with all this happening, I would say ITER will see the first plasma 5-6 years from now, though there could be a lot of challenges in terms of other complexities and all, but it is really a happening project. Since it is an experimental project, all the member countries will get the technology. So our aim is to get the technology and replicate such devices in India so that we can convert that into a power generating fusion device. Right now it is only an experimental thing.
I mean, Niraj, this must be so exciting, and your company is involved as well.
Right.
I mean, it's really to be part of history when we look at what's going on here.
Absolutely. So in addition to working with ITER, where we supply or we're qualified for materials, ITER's and Shaurya alluded to it, that what we're seeing is we're seeing far greater trajectory for private fusion reactors. We work with one of the largest privately funded reactors in the US called Commonwealth Fusion System, which is building out Spark, and we've already supplied 20,000 components. I have some show and tell pieces. So these are things that go in. to the reactors for ITER, for any fusion reactor. These are neutron shielding.
Hold them up here. He wants to get a nice picture
neutron
there.
shielding components that are used in there. The point being that we're seeing great trajectory, great momentum towards these, and I think from our perspective, it's not just ITER, but the activity that we're seeing around private reactors, and not just in the US. We're seeing a lot of that in Europe, in the UK, in Germany, in France, and of course in India with Pranos. So we're hoping that the private sector kind of leverages off the basic science that is being done in a project like ITER, and then builds out something which is maybe smaller than ITER, but just more faster to actually generate or break the engineering barriers there. So it's quite exciting.
It is indeed. Shaurya, in your position here with Panos Fusion, I mean, again, you're looking more on the startup side, so you must watch all of this and just watch in awe in many ways. But then what are you going to do? Try and run ahead of it?
Right. I would say ITER's been a blueprint of sorts for us in terms of what to do and what to do differently. ITER's extremely large and extremely ambitious and extremely expensive. Now, for a private company to enter into this space, specifically a startup, that's not the trajectory we take, but we learn from that trajectory. So our partnership with ITER gives us access to design documents, gives us access to technology that's been done, so that we don't, as a private entity, spend time in research. We're able to take things that have been researched, data that has been collected, and then translate that into a commercial product. We've seen that with the software system that we've developed and the prototype that we've been building right now. We're soon moving to high temperature superconducting magnets, which ITER doesn't have, by the way. Just because ITER is a long project, the magnets on that got decided pretty early on, but the state of the art right now is high temperature superconductors, which is which allows you to build reactors much smaller. And when I say much smaller, you could build a reactor 1/10 the size of ITER with the same fusion performance.
But not as small as the more typical nuclear smaller reactors that we're seeing now. Not that size, no.
So
they'll be bigger than that.
They will be bigger, but the idea is what we're looking at is something around 50 megawatts, 50 to 200 megawatts, and the design philosophy that we're putting in from the design phase right itself is something that can fit into the back of a truck.
Okay.
So that the promise of fusion is essentially you can, well, it's going to be expensive for sure. Fusion energy is going to be expensive, but the applications are you're tapping into a new energy source. It can help with powering remote places. Most remote places in countries like India are only accessible by road. If your reactor is bigger than the width of the road, you really can't get to remote areas. So that's the design philosophy that we're working with for the software and the prototype that we've been working on.
Niraj, when we think about the first fusion plant, they're going to be custom built without a doubt here. But again, talk to me, it needs collaboration, it needs cooperation on such a huge scale. And it's great already we're seeing it among some of the big countries. But, you need to be involved in this in the design phase. I mean, are you getting in there as an Indian player to actually be part of the design and learning from that?
Yeah, absolutely. So I think as Shaurya mentioned, the real challenge for fusion, especially tokamak-driven fusion, is not the plasma physics part, but the manufacturing and the engineering portion. And as a result, what we have started doing with our customers, including CFS, is that we're involved when we're designing, when they're thinking of neutron shielding components and shapes, we're involved in helping them design shapes from a manufacturability perspective. What we don't want is a designer coming up with a design which is great on paper, but it's just impossible to make. And then you kind of go back to the drawing board. So we found that partnership very, very useful. And we're kind of taking that same method for all the other customers that we're working with. Unlike in ITER, where things got decided way before in isolation, and they've had a lot of challenges for manufacturing because someone decided to shape without talking to a manufacturer whether it's possible.
Right.
At least, and as Shaurya said, one of the things that ITER has done is not only are they sharing their success stories, but they're also sharing their failures for people to see what they did wrong and not repeat the same mistakes.
And I think that learning process is going to be so important. You want to come in here, please? Go
Yes,
ahead.
I mean, I was specifically pointing out that, both Raghavan and Neeraj represent the love for standardization
Yes,
that goes
yes.
into a mature industry. And that's something we're seeing signs of that already or with projects that like ITER and CFS's work.
I mean, how far away from that standardization? Because we look at, the industrial sort of process. We need standardization in place. It can't be.
So from a material specification perspective, it's standardized.
Okay.
Right? So everyone's following the same spec. Now the only thing we're designing is shapes and pricing. We've reached that stage already where there's no longer experimentation, at least for boron carbide, that's happening.
Raghavan, when we look at, there's mature frameworks, I think, for conventional energy here in India, without a doubt. But fusion's going to be different. When we look at regulatory environment, when we look at, the governance, the safety, where do we, what can you advise on that? It's going to be a bit different.
Yeah, definitely. But in India, if you see, the nuclear sector is managed by Department of Atomic Energy and Institute of Plasma Research, particularly for the fusion. So these two government agencies, actually in India, the fusion R&D is backed by the government. It's fully funded by the government. And the next approach is we are focusing more on ITER at this point of time to learn from ITER and implement in India. So first is government-backed R&D. Second one is see the results, early results of ITER. And also we have few fusion reactor in Institute of Plasma Research, SST1, Aditya, Tokamak. So conduct more experiments and learn from the existing tokamaks so that we will be able to improve and design a new tokamak for the future. So India is also looking at fusion, fission as a hybrid so that we'll be able to make the fuel efficiency better in the existing fission reactors so that it can be an integrated approach. So government is also focusing on fusion, fission, hybrid approach.
And when you have all of that data, I guess, and all of the research and development that's happening here, the encouragement of the government, the collaboration with all of those other countries, it's so important. I think, maybe two of you can pick up on this. Nobody will argue with the physics, that's in place. But when we look at the engineering, the operations, the design, maintenance, all of that, is all that planned ahead? Maybe.
Well, so I think what's important is that, at least what our experience with fusion has been, that they're drawing from capabilities that already exist, both in fission and even in oil and gas, right? So if you're looking at fabrication facilities, forging capabilities, that already exists. So it's not, because you're no longer doing the nuclear physics part of it, it's all actually manufacturing. So what we are seeing with CFS is their vessels are being made in Europe by large oil and gas players. So it's not really restricted to a specific supply chain. So from my perspective, it's an exciting time for India. India is well positioned to be at the forefront of being in the fusion supply chain.
Talk to me just a little bit about, we need a lot of capital, whether it be the work that's going on in France and the US and UK, it doesn't matter. Money is, important in this, and governments are certainly helping it. You need, ecosystem partners. You need utilities. You need EPCs. Everybody has to be involved in this. And maybe the three of you can address this, what would be the ideal coalition, in terms of getting the right partners on board? And where are maybe the tough ones to convince and bring it in? And is that maybe civil society, or do you think we're happy enough there?
Well, I think for civil society, what the US and UK have done, like I mentioned, is remove the word nuclear out of it, right? So they don't call it nuclear anymore. Civil society doesn't really get bothered by it because fundamentally it is different from a nuclear fission reactor. What we really need is just collaboration between industries. Right, so learning best practices from oil and gas, best practices from fission. So having that interplay is important, and I'm actually very excited. And when you talk of capital, if you see besides ITER, if you look at the US and Europe, there's a lot of risk capital from venture capitalists. CFS is funded, has $2 billion in capital, which is
It's 3 billion
$3
now.
billion now.
Okay, good.
So they have enough money to do it. The Germans have raised a lot of money. Proxima has raised 200 million. So I don't think capital is a constraint at this stage.
Well, I mean, that's such an exciting development in the energy space. And again, talk to me, in terms of the work that you will be doing on the smaller side, the coalition partners that you really want to have on board.
Right. So in terms of the difficulty of we've in our journey convinced the hardest people to convince, which is venture capital in India. Because the risk-taking capability and just the vision of venture capital in India is changing. How we've been able to do that is build a pathway which de-risks a technology over a period of time while creating something of value. Every time you talk about fusion, you get asked the same question, hey, but it's 20 years away, it's 30 years away, when will we light the first bulb? But that's not how you really make money out of technology anyway. What's important is we stop looking at fusion like a destination problem, but see what are the developments happening on the way.
Along the way,
Yes, because the first money or the first commercialization out of fusion is not going to be from lighting bulbs. It's going to be from other pieces of technology, from magnets to cryolines to even neutron sources, as pointed out in the fusion-fission hybrid. So we've kind of convinced the hardest people to convince. Governments are already on it. We do believe that once a certain technology de-risking happens, the Department of Atomic Energy and the Indian government is aligned to put in and understand that this is going to be a national mission, because within 2030, we will see net gain reactors across the world on the east and the west. And at that point of time, we shouldn't be at a point where we're just starting. We should be probably 60-70% in it to be able to then deliver. And it has to be a joint effort. I mean, the panel here says a lot. We represent a small, iterative, fast-moving space. And both these gentlemen, they represent the grounding pillars of building in India in many ways.
Yeah, and indeed, having that foundation there. I have to begin to wrap this up. So, Neeraj, maybe I'll get you to sort of give us a bit of a call to action to maybe, yes, the energy industry, but also maybe to a wider population to maybe wake up and realize how real this is.
I would say, and as Shaurya mentioned, that countries that do not get onto the fusion bandwagon are going to be significantly disadvantaged. So you don't want to be left behind, and you can leapfrog. Even if countries don't have a nuclear program, they can actually leverage off each other or kind of collaborative work with countries like India and build their own fusion program. It's clean energy. Eventually, it'll be economical energy. And I think it's important to have that. So I think I can't overemphasize how important fusion is going to be for the world.
It's literally unlocking the power of the universe. Every single source of power that you see in the universe is second hand to fusion, right? The universe naturally chooses fusion as the process, as the most efficient process to make.
And I think somewhere that's where people don't realize that almost this is the most natural.
Yeah, everything from solar, wind, fission, even oil and gas, it's all second hand to fusion.
Actually, the energy from the solar, that is also fusion, the main the source of energy. Actually, what we are telling, even for the ITER project, we used to tell, bringing the sun to the earth. We are going to set up what powers sun we are going to make on the earth. So that is the thing. You asked about the challenge. I would say, though nuclear fusion, though the nuclear technology is not there, still it is governed by the nuclear regulator and the nuclear design. So that we need to have a separate regulation or design standards for nuclear fusion. That is one. And also standardize the design. The moment we standardize similar to the small modular reactor we talk about in the fission, we should have a small modular fusion reactor, so that once we standardize and we mass produce, definitely it will be economically viable. Ultimately, if it is for an electricity application, power generating application, cost of electricity, the levelized cost of electricity, that would decide whether the technology is viable so that it can
So
be
your
implemented.
big call to action, what do you want it to be?
So I would say accelerate R&D on material, design, standardize, and go for large-scale implementation, make the technology viable, then it will be. So we need to do all these things to make the technology viable. Otherwise, fusion research has been happening for the last 40, 45 years, right? So last 5 years, tremendous work has been
Yes,
done in the
yes.
last 5 years, but still a lot of work to be done to make it commercially viable.
Shaurya, I'll give you the closing word here in terms of, particularly in that startup phase and the possibilities that are there for so many companies, I think, and the impact on so many other industries. What would you do a call for action in that? And again, do we need to also be educating, our politicians, our scientists, or are they there yet, and our people in general?
Right. We probably need a generation of people who are believers and who understand that we have very few energy sources left with us to explore. Fusion actually answers a lot. It's a civilizational shift. I can't emphasize more on the fact that this is coming, and we need to be at the forefront of when this actually hits us, because it's going to be one piece of technology we just suddenly have in our lives, and then we wonder, okay, when did this happen?
Wow.
But that being said, I feel like fusion energy needs not just believers, but also people working in it, because it's such a big multi-physics problem. You need people from, people who design screws, nuts, and bolts, to welders, to, and ITER is a big example of the kind of effort it takes. So I would say keep an eye out for the next 5 years. Is going to be groundbreaking for energy transition.
But that's very exciting. And of course, we've already seen transformation. And even as we were saying, Raghavan, it's such an exciting time for engineers. It's not that they've been bored all this time, but it must be really the most exciting time. So well done to all of you. I think the great work that you're already doing it, and indeed for India to be involved in this project, is quite phenomenal. Ladies and gentlemen, thank my great team of visionaries here, because really that's what we're looking at. Dr. Shaurya, thank you so much. Raghavan and Niraj
Thank you.
Bukhanwala, thank you
Thank you.
again. Thank you. And to all of you, thank you.